let's get started. Numerical data, our first topic. So essentially, we're dealing with several types of numbers. First and foremost, integers. They're whole numbers. They help us count stuff. Next, floating point numbers. So these have decimal points, and they're used for more precise calculations. And finally, there are binary, hexadecimal, and octal numbers. Now, computers only use binary, and there are several shortcuts that we've developed to deal with binary. In Python, you do not really, other than hexadecimal, have to worry about many of them. But if you're in the world of machine language and microcontrollers, this is more of an issue. So let's get started with integers. So integers, they can be positive or negative, but they are always whole numbers. In the slide right here, you have the creation of an integer. You've got an example of a negative integer. You have print type, basically checks the type. And if we have created 49, that's an integer, and negative 35 is also the same type. Class integer. So, one more thing. In other programming languages, you have special data types for very, very large numbers, like long or double. In Python, an integer is as big as it needs to be. So essentially, Python can accommodate integers with, I don't even know, if those are acceptable, that must be quadrillion. So, next, we're going to look at floating point numbers. A floating point number, as I had mentioned before, is just a number with a decimal place. So if you create n right here, and n is a floating point number, it's 3.333, you can print it. You can actually use different types of floating point numbers like constants from the math module. This is an example of pi. And you can always check what type they are. Anything with a decimal point is pretty much always going to be type floating point. So, integers and floating points can be converted between each other. Obviously, when you convert from a floating point to an integer, you're going to round up or down, whichever way is closer. So you're going to lose some precision. When you convert an integer to a floating point, you're essentially going to add a .0. So even if you created, in this instant, 3.0, that wouldn't be an integer. The second you create a decimal point, that is a floating point number. So other types of numbers: binary, hexadecimal, and octal numbers. First up, binary. Now, binary is essentially how computers work. They add up numbers that are made up of ones and zeros. These ones and zeros represent powers of the number 2. So if you look at, for example, 111, that is 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2. 1 plus 2 plus 4 makes 7. So 2 to the power of 0, there's none of them, but 2 to the power of 1, there's one of them, that makes 2. So typically the computers nowadays deal with very large binary numbers, like the examples we had, are just 2 digits. They deal with 32-digit and 64-digit binary numbers. So my computer is a 64-bit. That's where the bits come from. Bits, each bit is a 1 or a 0. And you might hear the word byte. A byte is 8 binary numbers. And you're going to see why that's relevant in a second. Because the other types of numbers that computers deal with, these are a bit archaic. So in older computers, you would maybe use hexadecimal to reference memory addresses and registers. Now this is more machine language and microcontrollers, but you might come across them. In fact, you certainly will come across them when it comes to colors. So the RGB color system is usually encoded with 3 numbers between 0 and 255, and the shorthand for that is 3 hexadecimal numbers. These are always 2 digits, so that's a lot easier. Hexadecimal numbers work on the base of 16, so you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is A, 11 is B, 12 is C, D is 13, E is 14, and F, conveniently, is 15. So 0x denotes hexadecimal, just like 0b denotes binary. F is 15. That's a really complex one, because 3 digits. But AF, for example, basically you get A, convert that to binary, and get F, convert that to binary. So A is 10. In binary, it's 1010, and F is pretty much the biggest 4-digit binary number. So F is 1111. And if they combine one big binary number, that number evaluates to 175. So the range for these 2-letter hexadecimals is 0 to 255, which is a byte, which is how colors are encoded in RGB systems, which is where you're going to come across hexadecimals. So last but not least, well, perhaps the least, are octal numbers. Octal numbers have a base of 8, so you count 0, 1, 2, 3, 4, 5, 6, 7, then you jump to the next one. So in octal, 8 is written as 10, like our number is 16, decimal number is 16 would be 20, and then if you added 8 more to that, that would be 30. And octals are really, they're just used in old 8-bit computers and maybe some old 8-bit microcontrollers that are still around. So I came across them tangentially when I did my degree and worked with microcontrollers something like 13, 14 years ago. So octal numbers, an interesting piece of history. You should know though that their sort of notation in Python is this 000 lowercase o. That stands for octal. So we're done with that, and now we're going to have a more practical look into binary and hexadecimal numbers and do some conversions with them in Python. So I'm going to start this by just creating a new file. I figure it's good that we do this sometimes. And since we're going to be playing with conversion of various number types, I'm just going to call this file converter. So let's start with creating an integer. Let's go num equals the 33. Now that's an integer. Now we can convert that using your standard type conversion to binary, octal, hexadecimal. Maybe that way, like have them in order. So we can print bin num. And that ought to print the binary. So if we do that, I'm not sure, no such file or directory. Can I run it again? That works. So 0b10001. So obviously that guy here is 2 to the power of 0, so that's 1 plus, and 2 to the power 1, 2, 3, 4, 5. 1 plus 2 to the power of 5, that's 32 plus 1, 33. That clearly works. So similarly, we can go to octal. Print oct of num, and that ought to be, yeah, that's the octal sign, 41. So that'd be 8 times 4 plus, yeah, 32 plus 1. 8 times 4, see, 4 plus 1. Works. And we can print hexadecimal, hex of num. So that is 21. 2 times 16 plus 1 is 33. And just out of curiosity, we can also print float. Float num, and that should just give us 33.0. There you have it. So now that we've converted it from an integer to all of these, let's try perhaps converting from like binary back to an integer. So a binary number is right here, but remember 0b is just a symbol, so this is the binary number, and I'll show you how the conversion works. It's actually a little bit complicated. So if you say I equals to int, that's typecasting something to an integer. Now we can paste this binary number, and we can say comma the base that it is, but this will still give us an error, and actually quite an interesting one. Int can't convert to a non-string explicit base. You actually have to present the binary hexadecimal or decimal number as a string. Then that'll be saved as I. Remember, I is an integer, so when we print I, we should get 33. There you have it. So this should work. I mean, if this is the octal number, we could have gone base 8 and 41. So we could have written 41 here, base 8, and we could have printed that, and that will come up with 33. So right now what I want to do is turn this little insight into something useful, a color converter for hex colors. Now, let's just take an example of a hex color. Example hex color. And I'm going to take DC 143C. I don't actually remember what it was, but you can pretty much just enter it into Google and find out. So let's see if we can convert a string like that into basically red, green, and blue. And we're going to find out what the color is in a second. So instead of basically having something like that, you can take red, green, and blue, G and B. So these three are going to have to be replaced with DC 14 and 3C. And then we can print RG and B. So let's have a look. Yeah, 220, 20, 60. It's a very sort of reddish RG. So G is very low. So it's red-blue. It's a sort of very reddish, slightly purple color. And obviously you can enter any three colors this way. If the hex is presented like that, you'd be able to chop it up into a string. But just as an example of looking at values like binary, octal, and hexadecimal, this is a practical way to convert them back to integers. All right, let's get back to the lesson.